In this section, we're going to begin our journey into 3 dimensions, right? So far, you've done all of your math, including calculus, just in 2 dimensions. And so we're going to kind of move beyond that. Of course, if we're in 2 dimensions, we're always talking about the xy plane, or the x-axis and the y-axis put together. So now we're just going to make a 3rd axis here, and we're going to call it the z-axis. And so when we have, instead of ordered pairs, now we're going to have ordered triples that we designate as x, comma, y, comma, z. And then, of course, we'll still call the place where all of them intersect the origin. All right, so down here, the thing I want to point out is that when you are trying to accurately represent a point in 3-dimensional space, it's important to parallel the axis that you are trying to represent. And what I mean by that is, so if I have a comma b comma c, I know that I need to go out a in my x, and so that's easy. I just go along the x-axis until I get out to here to a. But then when I am going to go b in the y direction, I need to parallel the y-axis, and then as I go in the z direction, I need to parallel the z-axis in order to accurately represent where this point actually ends up. All right. So a lot of times it can be helpful in terms of locating things to think about the projection of a point onto a 2-dimensional surface. So if you take the point ABC that we were just talking about, you can project it onto the YZ plane. So we call this thing the YZ plane over here. I can project it onto the XZ plane, or I can project it down to the XY plane. Okay, so you'll hear us refer to these 3 different planes. The XY plane we're of course very used to, because that's all we used to be looking at. But now we'll talk about 3 different planes, right? So the one formed by Z and X, the one formed by Z and Y, and then the one we've been working with all our lives, the one formed by X and Y. All right, and then just one little piece of notation that we'll use to quickly make sure that we are all in agreement about whether we're working in 2 dimensions or 3 dimensions is, if we're working with ordered pairs in 2 dimensions, we'll use this symbol R2. It means, you think of it as the real number squared, or there's 2 of them. And then R3 is the 3-dimensional set of all ordered triples. All right, so we're actually going to do some preliminary graphing here. This is not the only section we'll be doing graphing, and we'll be working on it throughout the course. So we'll have plenty of chance to practice, but I'll try to give you some principles that'll help you in this area of graphing in 3 dimensions, because I know that's new for us. But in addition to graphing, we also have to make sure that we know how to make sense of equations. So I'm going to start us off here with a really simple equation, y equals 4. Okay, so y equals 4. So now you might kind of find this curious, because you would think, okay, I'm in 3 dimensions, so shouldn't my equation have x's, y's, and z's in it? Well, what I would have you do is remember, okay, we're talking about an R3, right? But let's, over on the side here, in R2, what does y equals 4 mean? Well, remember that that's a horizontal line, right? Up here at 4. And it means that no matter what x is, y is going to be 4. So that's what it means in R2. So here what we can say is, if x and z are not present, we can say that y equals 4 no matter what x and z are. Okay, that would be one way to look at that. All right, so one way to start this might be to say, well, let's maybe just kind of freeze one of these variables in place. And I think it makes sense, since z is the one that's kind of new to us, maybe let's freeze that in place. So suppose that z equals 0, just to start with. Just to keep this real simple. Suppose z equals 0. So if z equals 0, I'm just going to be graphing in the xy plane. Well, if z equals 0, aren't we just in this case up here, right? We're in the xy plane, and we know that y is supposed to equal 4. So what I can do is I can go out 4. Okay, and then I know up here y equals 4 is parallel to the x-axis. Well, I'm also going to stay parallel to the x-axis, but based upon the way this graph is oriented, in order to do that, I'm going to have to really try to go at this angle here, right, and stay parallel to that x-axis. Okay. So if I want z equals 0, that's the line I just drew. Okay. What if I let x equal 0? Okay. Well, if x equals 0, then what we're supposed to be saying is that y equals 4 no matter what z is. Okay. So it's the same idea. So what I'm going to try to do is just stay in the yz plane, and I'm just going to go straight up from here. And I'm trying the best I can, at least, to parallel the z-axis. It'd be easier with a straight edge. Okay. And so now I think we can kind of start to see this. We have a line here and we have a line here, but at the same time, we kind of have lines everywhere, right? We know that no matter what x and z you pick, so if you give me any old xz over here, I know that y has got to be 4, okay? So what I'm thinking is that I should be able to kind of connect this stuff up. And I'm going to try, what I'm going to do is I'm going to draw this line here, but I'm going to stay parallel to the line I already drew down there. And then I'm going to stay parallel vertically also. Okay, and now I'm going to try to stay parallel to the x-axis once again. So the lines that I'm drawing in this direction, I'm trying to stay parallel to the x-axis. The lines I'm going up and down, I'm trying to stay parallel to the z-axis. All the while maintaining the relationship that y should be equal to 4 at all times. Okay, now what does this form? Well, this definitely forms a plane, right? So this is flat. If y is always 4, that should be flat. Now, does this plane extend beyond the boundaries that I drew? Of course it does. But we got to put boundaries on to give our eyes something to lock onto. So yes, we know that it continues to go on, but basically drew this little window here is what we, now are there really lines here? No, right? This is just this solid sheet that's right here. But having some of those lines and those contours there, they help us to visualize what's actually happening. All right, let's take a look at another one here. Here's another one where they kind of want us to figure out what this thing's supposed to be before we actually graph it. So x squared plus y equals 4. So again, I'm only involving 2 of the variables this time. I'm missing z. All right. Now, if this were just in the xy plane, right? If we weren't in 3 dimensions, I think we would all do this, right? We'd want to get the y all by itself. And the nice thing is, when we say if we were in the xy plane, this is what we would do. We would just graph this thing. Okay, well, we can do that. That's only going to be a small part of the graph that we create, but it'll probably be a helpful thing to go ahead and draw this. So y equals 4 minus x squared, you know, over on the side here, there's nothing wrong with just go ahead and drawing the two-dimensional version of it. That's a very bad y-axis there. So here's y, here's x, right? And we know, okay, we're going to shift up 4, and then it's going to be a parabola that opens down, right? Okay, I really need to clean that up. I think that's looking bad. I think it'll be worth our time to do this right. Okay, and let me do another color here. So I know that I'm going to go up 4. And you know, when we're graphing two-dimensionally, just like when we're graphing three-dimensionally, it'll be true as well. We kind of want to be accurate when we cross axes. So let's remember what the x-intercepts are for this. We can find x-intercepts here with a three-dimensional graph, just like we can a 2. So I'm going to put 0 equal to y. So that means x squared equals 4. So that means x equals plus or minus 2. So up on our little two-dimensional graph here, I know that I'm crossing the x-axis at -2 and 2. So this is my parabola. Okay, so that is in the xy plane. So I suggest that let's let that be the very first thing we draw over here. So I go up 4 on the y-axis. There's my first spot. And then I'm going to go 2 in the x direction. That gives me one there and gives me one there. So, and then I'm going to try my best to kind of show a parabola and what I kind of think it would look like looking at it from an angle in 3D space. Okay? So, that's part of it. But understand that when we say that y equals 4 minus x squared, this is true no matter what z is, right? Since z is absent from the formula, that must mean the z doesn't matter. So in other words, this formula is true for all z values. So let's go up here. How about we go up quite a ways, all the way up to z equals 6. Okay, and let's let that be where we sketch things. Okay, what we're saying is that we should have the same pattern up here at z equals 6. Okay, so what I want then is this point to go up to 6. Now what I do is I don't go straight across like this. That is not where that point is. I am going to, either in my mind or maybe very lightly with my pencil, I am going to try to parallel the y-axis and then go parallel to the z-axis up from there to put that point. So do you see how it actually, if I went straight that way, it looks like it's hitting at about, you know, I don't know, 5 and, you know, 5.7, 5.8. But this is at a height of z equals 7. All right, and we can do the same thing here. So I want to kind of parallel the x-axis and I want to parallel the z-axis, and that's where that point gets put. And then same thing there, continue to parallel the x-axis with maybe just really light penciling or something, and then go straight up from there, try to parallel it, and so there, that's where you're at. And then you're going to, again, just try your best to show what that parabola would look like. Okay, but of course between these here, there's lots more parabolas, right? So this is really forming, you know, this sheet here, and I can do this. You know, I could go down as well, right? I could go down 3, 4, 5. I could go 5 down, and I could just play the same game. So kind of parallel the y-axis, parallel the z-axis, parallel the x-axis, parallel the z-axis. Okay, and so I think this is probably plenty, but we definitely get the idea. Now what I'm going to do is, I understand that the parabolas don't actually stop here, do they? Right? They keep going. But just like in our plane above, we kind of have to, at some point, stop it so that our brain can really process what it is that's going on. And so I'm going to kind of connect these up here, right? I'm going to connect here, but I know that that's really supposed to be hidden from me, right? So I'm going to stop drawing that, and then I'm going to connect these up. Okay. And then I do know that these ones back here are actually hidden from me. So let me do this. Let's get a smaller circle there. You know, it's always kind of good form to kind of do dashes when things are supposed to be hidden, right? All right, and so that right there gives us our gives us a picture of what's going on. And I guess I could, you know, if I wanted to, I could also kind of dash here, so you know, maybe a little more clear how that's going. But we can definitely see how this, you know, the shape of this thing, right? This is a parabolic sheet, and I can clearly see what's going on there. But notice how important it was to have those parallels as we are kind of projecting points up, down, side to side, and everything. All right. One of the things that we're going to need to do is be able to calculate distance in three-dimensional space. Okay, so what I'm going to have us do here is look at this scenario here, where you can also see what's happening in the familiar XY plane. So if I go over left 3 in the X and then up 4 in the Y, we should be familiar with how to calculate the distance here, right? Straight from the origin to the point -3, 4, and yes, it's comma 0, right? But if we were just thinking in 2 dimensions, we could definitely calculate that distance, right? So that's going to be, and we'll call it R. So we know that R is equal to the square root of 4 squared plus -3 squared, which is the square root of 25, which is 5. Okay, so R equals 5. Now, if I wanted to then calculate the distance from the origin to this point, the point -3, 4, 5, let's switch up our, let's go ahead and make that red, I guess. Then I'm asking for this distance here, right? Okay, but what you notice though is I've just made another triangle here. It's got R equals 5 here, and then R equals 5 there. So again, with the same reasoning as before, if I call this D, we can see that D is equal to the square root of, okay, it's going to be 5 squared plus 5 squared. Okay, now this 5 squared is the Z, right? But where did this 5 come from, right? This 5 came from the square root of 4 squared plus -3 squared. Okay, so here we have Z squared, here we have the square root of 4 squared plus -3 squared, but of course the square and the square root undo each other, right? So the distance just ended up being distance from the origin, that is, just ended up being 4 squared plus negative 3 squared plus z squared. So this is just the extension of the Pythagorean theorem in 2 dimensions, is that in general, what we can do is just take the square root of x squared plus y squared plus z squared to find that distance from the origin. But then more generally, we're not always going from the origin, right? A lot of times we want to go between 2 points. So we just take the distance formula we know from 2 dimensions, which is the difference in x's squared plus the difference in y squared, take the square root, and just add the difference in z squared. So if I want an example 4 here to find the distance between these 2 points, it really is just as straightforward as plugging these values in. So one really big square root here. So if I think of q as x as the second one and p as the first, this is 4 minus negative 2 squared plus negative 3 minus 3 squared plus negative 1 minus negative 5 squared. So here we've got 36, right? Here we have 36, and here we have 16. So this is the square root of 88, which is square root of 4 times 22. So that'd be 2 roots of 22 is the distance between those 2 points. All right. Now, one of the things that you definitely studied in, well, in probably a lot of classes actually, is circles in 2 dimensions. So, of course, it's appropriate for us to study the equivalent in 3 dimensions, which is, of course, the sphere, right? And so then, not surprisingly, remember that the circles equation is just all built off of the distance formula, really. Or I guess you could say it the other way, the distance formula is built off a circle. But then if we're talking about a sphere, we just add a z component as well. So remember, for circles, it was x minus h squared plus y minus k squared equals r squared, where h and k were the center. Okay, well now hkl is the center, and l, z minus l squared is added to the equation. And then if you have a sphere centered at the origin, it's just x squared plus y squared plus z squared equals the radius squared. So one of the things you did do with spheres, with circles before, is you would complete the square in order to be able to see what the radius is and what the center is. And so we can do that here with spheres. And so this is just a little reminder. I know you've done this at some point in the past where you're trying to put this in this form, right? If you can put it in this form, then you can see the center and the radius. So of course, if I want to put all these x terms and get them in this form, I should start by gathering them all together. So 2x squared plus x, put those together. And then we have plus 2y squared minus 4y. And then we have plus 2z squared plus 6z. And we know that we want stuff on the other side, so I'm going to subtract 1/8 from both sides. Okay, now what we always do like is when we complete the square, it sure is nice if, actually I shouldn't say it sure is nice, we want to get rid of the coefficient that's out in front. And so if there's a coefficient in front of your squared terms, we know that we got to get rid of those, and so we can multiply by 1/2 over here, and that's fine as long as I multiply by 1/2 over here as well. And so I distribute that through, and I get x squared plus 1/2 x. And then when completing the square, we know we got to add something, right? So I'm going to leave a little blank here. And then I'm going to say plus y squared minus 2y plus something, and then plus z squared plus 3z plus a little something, and that's going to be equal to negative 1/16 plus all these things that we are going to decide to add on the left side, right, to balance everything out. And so when you complete the square, let's start with this one. This one's easier. You always chop the middle in half and square it. And the reason that you do that is you're saying to yourself, I know I need these to factor into something that would where the outside and inside would add to make this and multiply by itself to make that. So the only thing that can add to make negative 2y is negative 1 and negative 1. And so similarly here, I'm going to chop that in half, which is a fourth, okay, and then square it. Okay, so why does that work well? Because I need to make the outside and inside equal a half when I add them together. So what would do that? A fourth and a fourth. And then with the z, chop 3 in half. You'll just get 3 halves and squared, because z plus 3 halves times z plus 3 halves does the job of giving you this middle term. And so we're adding 1/4 squared, which is 1/16. We're adding negative 1 squared, which is 1. And we're adding 3 halves squared, which is 9/4. So this all becomes x plus a quarter squared plus y minus 1 squared plus z plus 3 halves squared. And that's equal to 1 plus 9/4, right? So that would be 4/4 plus 9/4. So that's going to equal 13/4. So this is our proper form of a sphere, and I can see that my center is going to be negative a quarter, 1, negative 3 halves. But then my radius, be careful, the radius, right, is not this. This is the radius squared. So the radius is going to be the square root of 13/4, which is the square root of 13/2. So that's our radius. All right, so on this last page, we're going to address inequalities in 3 dimensions and try to get a sense for what's happening with these. So here it says, what region in R3 is represented by these inequalities? So they give us, on the one hand, x squared plus y squared is less than or equal to z squared. And then they're saying that z is between 0 and 4. Okay. So like we did earlier when we graphed a few things, let's look at some particular values of z. So to start off with, let's think about z equals 0. So if we do z equals 0, then we're saying x squared plus y squared is less than or equal to 0, which is kind of an awkward thing because the only way that would work is if both x and y are 0. So for that case, all I can do is put a little dot right here. So when z is 0, x and y have to be 0. Okay, let's try z equals 1. So if z equals 1, then we're saying x squared plus y squared is less than or equal to 1. Okay, so if we were in 2 dimensions, this would be a circle of radius 1. Okay, right, we would make a circle, we'd give it a radius of 1. But because it's an inequality, we would fill it in, right? Everything inside of 1. So we want to do the same thing right here. Now this is a little bit tricky, but what I want to do then is I want to make a circle, but I want to make it in the plane where z equals 1. So I'm going to put 1 here, and I'm also going to put 1 out here, 1 over here, and 1 out here, and back there. Okay, so I've got those. Now, what am I going to do though? I'm going to parallel, right, in order to place my points. So these 2 points are the ones that are directly above the x-axis. And I'm going to parallel my z here, parallel my y here. Okay, and so here's what I come to the conclusion of. I've got a circle of radius 1. Looks something like that. Not perfect, okay, but that's my circle of radius 1. Doing my best to graph that. Let's jump up to z equals 4. So that's x squared plus y squared is less than or equal to 4. Okay, but that means that the radius is 2, so this is the circle of radius 4 squared is what I meant to say. So that's the circle, 4, so that would be 16. So this is a circle of radius 4. I was kind of going to sleep there. So here was 1, right? Here's z equals 2, z equals 3, z equals 4. Okay, so same thing. I want to go now out 4 in every direction. And I want to do that same parallel game, right? Kind of try to parallel and see how now I'm kind of trying to graduate to maybe not actually putting them down. I'm just trying to kind of parallel the appropriate axes. So continue to parallel here, stop right above it, parallel here, stop right above it. And so here's our and you can see why it's so hard to graph in 3 dimensions, because see how I kind of just covered up part of my z equals 1 circle? All right, so, I can't really emulate this here, but it's nice if I can, kind of draw really lightly. Okay, so what is this? We also had circles of radius 3 and radius 2. So I would think, kind of like on my parabolic sheet that I had before, it'd be nice to kind of connect up some of these points that I did. So let's connect these up as well. And so you know what this is looking like to me? This is looking like a cone. So it turns out that this, anytime you have this, and by the way, it's less than or equal to, so I'm a little leery to color it in blue, so maybe I'll color it in something nice and light so I don't, right? It's everything inside of here, right? So this would be described as the region inside of a cone. Okay. Anytime you have x squared plus y squared equals z squared, that's a cone. And then when you have less than or equal to, that's what makes us actually fill it in. All right. So let me go down to this last example. So this asks me to write the inequality and describe this region. It says the right circular cylinder of height 4 and radius 3 is bounded between the xz plane and the vertical plane, y equals 4. Okay, so a right circular cylinder with a height of 4 and radius of 3 is bounded between these. Now it's bounded with a vertical plane, right? So here's what this means. This right circular cylinder, we can all picture that in our mind, but the height of a cylinder, right, is, the height of a cylinder is, of course, this, and usually we have our cylinders sitting upright. But of course, in this case, if it's a vertical plane at y equals 4 and xz is this plane, then those boundaries must be where the flat parts are. So my height actually lies this way. So the height is 4, so I'm going to go 4 in this direction. And it's a cylinder, so I know I've got a couple of circles to make. Okay, it's in the xz plane, so that's a radius of 3. Okay, this needs to be out a little further, I think. All right, so as I draw my circle, I'm just trying to visualize it being just in that xz plane. Trying to visualize what that would look like. So you can kind of see that circle that's lying in that plane. Okay, and we kind of have these 4 important points that we did, right, where it crosses these axes. And so now I'm going to go over 4. So, remember, parallel the y-axis until you get directly under it. Parallel the y-axis until you get right about there. Right? Parallel the y-axis until you get right over that. Parallel the y-axis there. Right, until you've made a parallel with the x-axis. And so there's the other end of this cylinder that's kind of lying on its side. All right, and then we can kind of connect up some of these important points, right? All right, and I think that's good. I don't know that we need to clutter it up too much more than that. And so the right circular cylinder, height of 4, radius of 3, between the xz plane and the vertical plane. Okay, so what inequality is this? Okay, so we're saying that we want everything inside of here. Okay, so what kind of circle is this? This circle is x squared plus z squared needs to be less than or equal to 9 since the radius is 3. Okay, that gives me a filled in circle. Okay, but what it doesn't tell me is how far out to go. So we, in addition, need to also add, oh yeah, by the way, y should be between 0 and 4. And then that's what allows me to stop at the xz plane and then stop out here at y equals 4.